Morning, everybody. Today we're going to talk about the stellar life cycle, or the life cycle of stars. So again, as always, we're going to have a check for understanding after this inside Schoology. So make sure that you have read the notes and paid attention to this lecture. Okay, so here you see an HR diagram. We're going to be spending some more time talking about the HR diagram and how we organize stars and classify stars based on two characteristics: the absolute magnitude, which is the brightness, and then also the temperature. And one thing that I want to make sure that you understand is notice that the temperature on the x-axis actually goes down. So the stars that are on the side over here are hot, and the stars that are on the right side over here are cooler. They're still very hot, but they are much cooler than the ones on the left. But like I said, we'll get into that a little bit more later on. So let's just talk about some of the different stages that stars go through. So all stars start out or are born in a cloud of dust and gas called a stellar nebula. This is a picture of the Eagle Nebula in the constellation Orion, taken by the Hubble Space Telescope. So there is clouds of gas and dust spread out over the entire universe. And when gravity starts to pull these clouds of gas and dust together, it can become a star. And so as the mass of this cloud of gas and dust increases, and squeezes the material together, eventually it reaches a critical point where something called nuclear fusion begins, and that's where atoms start to be squeezed together to become new elements. So where hydrogen gets squeezed together to become helium, helium gets squeezed together to become beryllium. This is actually the origin of all the elements that we have on the periodic table. But it all starts out as hydrogen gas in the universe. And a star only becomes an actual star when that nuclear fusion begins and energy and light start to be produced. Generally speaking, there are two main life cycles of stars, and the factor that determines which life cycle they go into is completely based on their mass. So depending on how much gas and dust came together to form the star, if it's a small or average sized star, it's going to follow one path. If it's a massive star, anywhere from 3 times more than our sun, then it will follow a much more sped up life cycle. It won't last as long, and the death will be a lot more spectacular of that star. So when we talk about solar mass, we use the number 1 for our sun. And so if we say that a star has a solar mass of 3, that means that that star has 3 times the mass of our sun. Or if we say the solar mass is 10, that means that star has 10 times the mass of our sun. We always refer to it in comparison to our sun. So any star less than about 3 solar masses will spend almost all of its existence as a type of star called a main sequence star. That is where our sun is right now. It is in its main sequence stage of life. And scientists estimate that it's about midway through its life cycle. It's been around for about 5 billion years, and most astronomers believe that it will be around for another 5 billion years before it starts its end-of-life journey. Some gas and dust is pulled by gravity into the core. As the region of condensing matter heats up, it begins to glow. This is called a protostar. Temperature rises, nuclear fusion begins, and this is the actual birth of the star when nuclear fusion begins. And again, nuclear fusion is the atomic reaction that fuels stars. It's mostly converting hydrogen into helium. Stars that are up to 1.5 times the mass of our sun are called main sequence stars and will burn for a very long time. Of course, our sun is a medium-sized main sequence star, and of course, it is the closest star to us here on Earth. Now, towards the end of our sun's life cycle, when it stops burning hydrogen and all that's left in the sun is helium, then a red giant phase begins. And this is where our sun will start to expand and go from the size that you see here in the picture to something as big as something you see there on the right. This, of course, will swallow up Mercury, Venus, Earth, and probably Mars. Will be the death of the four probably inner planets. And then it will spend a certain amount of time as a red giant star. Okay, so this is towards the end of our life cycle of our sun or any main sequence star. They're very large and they can get up to 100 times larger than the size of the original star. Now, massive stars follow a much different path, anywhere between 1.5 to 3 times the mass of our sun. It has a greater mass, and so the more mass, the faster it burns through the helium. So its life cycle will be much shorter than a star like our sun. So you see two examples there of Betelgeuse and Antares. Those are massive stars, and they will burn through their gas the supply of hydrogen much faster. They will not live as long as main sequence stars, or medium-sized stars, I should say. And when they die at a much more spectacular fashion. A red supergiant is the next stage of these massive stars. So the next stage of our sun is a red giant. Massive stars become what we call red supergiants. They are much cooler than blue or white stars. This is a little contrary to popular belief. When we talk about the color of stars, that relates to their temperature, and red is actually cooler than blue stars. Blue stars are much hotter. White stars are also much hotter. So if you think about a flame, the blue part of any flame is hotter than the red or orange part. So red, anything that's red when we talk about stars are the coolest of the stars as far as temperature goes. Anything that's orange is a little bit hotter, white's a little bit hotter, and blue is the hottest when we talk about the different colors of stars. Okay? So when a massive star, a red supergiant, reaches the ultimate end, it will explode into something called a supernova. And at that point, even more so, the mass will determine what its next stage is. So when a supernova occurs, like you see there in the picture, that's a picture of a star known as Eta Carinae. And we actually caught an image of the supernova. And there are two different paths that the star can follow from this point. The white dwarf is the ultimate end of a star, a small star like ours. So the white dwarf is made up of pure carbon. It goes white hot with leftover heat, and it will drift in space while it slowly cools until ultimately all of the heat or all of the gas and carbon is burned out, and then it will become basically a black dwarf. A teaspoon of the material here would weigh as much as an elephant. So that tells you how the density of this material is extremely high. Again, the ultimate end of any medium-sized star like ours is a black dwarf. When the white dwarf star has cooled and completely burned all of its fuel and stops nuclear fusion, and it will drift through space as a frozen lump of carbon. This star is considered dead. Now, going back to the supernova, we mentioned that there are two options, two things that can happen after a supernova. Again, depending on its mass. If it's a lower mass supernova, then it will become what we call a neutron star. If the star is at least 1.5 but less than 9 times larger than the sun, the core left after the supernova will collapse into a neutron star. This is a star composed only of neutrons, and we should remember that from our chemistry unit. If the star is greater than 9 times bigger than our sun, then what will happen is the sun will, or the star will collapse in on itself and kind of turn itself inside out. And this becomes what we call a black hole, which is an extremely dense area with a very strong gravitational pull that even light cannot escape. Most astronomers believe that a black hole is what is at the center of all galaxies. It has enough gravity to hold billions of stars in orbit around it. So another phase in the life cycle after the red giant when we talk about smaller stars is what we call a planetary nebula. These form when a main sequence star grows into a red giant and then throws off its outer layers. The term planetary comes from the 19th century when astronomers saw what looked like a new planet in their primitive telescopes. It doesn't necessarily mean that planets will form here, but they just refer to it as a planetary nebula. Okay? All right, and so the last thing here is to understand the two different life cycles, again, based on the mass of the star. So here we have an average star. All stars start as a stellar nebula. Again, if it's a smaller mass star, it's going to follow this path, which means it'll live most of its life, about 10 billion years as an average size star. It will expand into what we call a red giant. When the outer layers blow off, we'll get what we call this planetary nebula. And then when all of this gas and dust moves away, we are left with a small white dwarf remnant of the original star. Now, if there's a lot of gas and dust, when we get up to 3 times the size of our sun, it becomes what we call a massive star. It's going to burn. It's also a main sequence star, but it's going to burn through that main sequence phase much faster. It will expand into a red supergiant, and then ultimately it will explode into something called a supernova. And then from that point, it will collapse on itself and either become a neutron star or turn itself inside out and become a black hole. Okay? So again, we'll talk more about this in class. And if you have any questions, as always, please make sure that you let me know. All right, guys, have a great day.